So we'll be doing one uh, example, which is exercise 1.2 of this workbook. So in this problem, we have a simply supported beam, and it has one load here and it has a triangular distributed load here. So it says consider the beam shown above. If the beam is cut at 3 meters, draw the internal force and internal moments on the left and right face to keep the beam in static equilibrium. So what we have to do is that we have to cut a section at 3 meters from the left side, and we have to calculate the internal forces in this case. So the first step is going to be drawing free body diagram. So if we draw a free body diagram, which would be a simply supported beam, and this is 1 meter, this is the distance which is 1 meter, and this is the distance which is 2 meter. So there's a force which is acting upward, which is a point load, and the magnitude of the force is 300 Newton. And also you have a triangular distributed load, and the maximum at this point, the value is 200 Newton per meter. So what we have to do is that we have to calculate the internal loads. But before we calculate the loads, internal loads, we have to calculate the reactions. So that's the first step. So the first step would be to calculate the reaction. So we can see we have a pin support here and we have a roller support here. So for a pin support, we usually see two type of reaction loads. And for a roller support, we have one reaction load. So I will call this point A, I will call this point B. So this force is called AX. This force is going to be called AY because it's acting along the y-axis if we assume that this is x-axis and this is y-axis. And this is the force B, which is acting vertically along y-axis. So I'm going to name it BY. So the first step would be to calculate the reaction loads. That's the first step. Step 1, calculate reaction loads. And how you can calculate the reaction loads is by using equilibrium equations. And there are three equilibrium equations. One is summation of forces along x-axis is equal to 0. Another one is summation of forces along y-axis is equal to 0. And then you can also take summation of moments. So the sign conventions we'll be using is that for forces which are acting along the positive x-axis or in this direction, we're gonna keep them positive, and the forces which are acting opposite are gonna be negative. And for the vertical forces or y-axis, we're gonna have positive if it's acting upward. And for moment, we're gonna assume anti-clockwise moment, which is going to be positive. So now what we can do is that we can start using those equilibrium equations and we can try to calculate what are the reaction loads. So the first equation I'm going to use is summation of forces acting horizontally is 0 because the beam is in equilibrium and all the forces which are acting in this direction is going to be positive. So how many forces there are along x-axis? I can only see one. This is along y-axis, this is along y-axis, this distributed load is also acting downward along y-axis, this is also acting along y-axis. So there's no other force. So we can safely say that AX is equal to 0. And the second equilibrium equation is summation of F of y is equal to 0. We'll assume all the forces acting upward is positive. So what we have to do, so for the external load, this is a point load, so this is fine, but this is a triangular load. So we have to convert this triangular load into an equivalent point load so that we can do the summation of forces. So how we can calculate this force? This force can be calculated by calculating the area of this load. And this is a triangle, so the area would be half into length into height. So the length is 2 meters, the height is 200, so it's going to be 100 Newton overall force. So I'm gonna put 100 Newton. That's the force, which is going to be, I guess it's not 100, it's 200. So that's the overall resultant force of this triangular distributed load. So now we can do the summation of forces. So I can see this AY, it's acting upward, so it's going to be positive. This 300 Newton force is also acting upward, so that's also positive. And this is 200, which is negative, and then you have another force which is upward, which is positive, is equal to 0. So if you solve this, you're going to get AY 300 minus 200. I'm going to put BY first here plus BY. 300 minus 200 is 100. So that's, but I cannot solve this further, so I'm going to use it as an equation later. So I've said this is an equation 1. I'm going to use it later. Now what we can do, we can use third equation with which is summation of moment is equal to 0. And we can take moments at any point. So let's just take moment at point A. So I'm going to take moment at point A, and anti-clockwise moment or counterclockwise moment is positive. So in this case, you have AX, moment arm is 0. You have AY, moment arm is 0. You have this force, 300 Newton, and it's gonna, so if this is the force, it's gonna rotate the beam. This is point A. This moment is gonna rotate the beam anti-clockwise or counterclockwise. So counterclockwise is positive. So we're gonna put positive sign. The force is 300 Newton, and the distance is 1. And then there's another force, this resultant force. This is going to rotate the beam in a clockwise, so I put minus sign. The force is 200 Newton, but we have to calculate the distance, the moment arm. So this is 1 plus, this is 1 plus, we have to also know what is the distance. So for a triangle, the resultant force is acting on a centroid. So this distance we all know is 2 by third of whatever the total length is. So in the total length in our case is 2. So this distance is 4 by 3. Is it okay? So that's the distance. So this is 1 meter, this is 1 meter, and this distance where the force is acting is 4 by 3. So you have 1 plus 1, so this distance plus this distance plus this distance. That's the total moment arm from where we are taking the moment. Plus 4 by 3. And then the last force is anti-clockwise positive. You have force By, and the distance between them is 1 plus 1 plus 2, which is 1 plus 1 plus 2 is equal to 0. So this is what I have. So this is going to be 0, this is going to be 0. If we solve further, you have 300 minus, if we solve this from a calculator, let's just say 200 into 1 plus 1 plus 4 by 3. I'm getting 3.33 plus By into 2 plus 1 plus 1, 4 is equal to 0. And then it's 300 minus 200 into 3.33. 666.66 plus 4By is equal to 0. 300 minus 666.6. Negative 366 plus 4By is equal to 0. 4By, we can move this to another side. You're going to get 366. And By would be 91.66 Newton. So that's what I'm getting for a vertical By. Now, the only force left for us is Ay. So we can use this equation 1. So if we use equation 1, we can calculate Ay. So Ay plus By plus 100 is equal to 0. That's the equation 1. So we're going to put this By, which we have calculated, here. So Ay plus 91.66 Newton plus 100 Newton is equal to 0. So Ay is equal to negative 191.66 Newton. So that's what I'm getting here. So I'm going to draw a free body diagram again. We had a simply supported beam. This distance is 2 meters. This distance is 1 meter. This distance is also 1 meter. We had two external loads. One was 300 Newton. Another one was a distributed triangular load with 200 Newton per meter. And as a reaction loads, this is what we got. So our AX is 0, but AY is negative. So we assumed in the start, we assumed AY, the direction we assumed was upward, but we got negative, so we're going to change the direction. So now we have changed the direction and the load is 191.66 Newton. And we got same positive sign, so we're going to keep the direction same, which is 91.66 Newton. So that's the reaction loads we got. Now we have to calculate the internal loads. So the question was, you go 3 meter from one side, from the left side, and you cut a section. And if you cut a section, you're going to expose the internal loads, and we will calculate those internal loads. So I'm going to draw free body diagram for sections. So I'm going to cut a section here, and then I'm going to expose the internal loads. So we know we have a load here, which is 300 Newton. We know we have an increasing load here. Which is, this point is 200 Newton per meter. And we have a section cuts here. So if you cut a section, you're going to expose internal loads. And these are the sign conventions of the internal load. So this is normal force, this is shear force, this is bending moment. This is normal force, this is shear force, this is bending moment. And these forces has to be like equal in magnitude. So either you calculate it from the left side or you calculate from the right side, you're gonna get same results. So I'm gonna call this section 1 and call this section 2. And we had this force, which is 191.66 Newton, and we have this force, which is 91.66 Newton. Also, we can see like the section was cut from here, so our triangular load also has been like halved. So half goes to section 1 and half went to section 2. So we also have to figure out how to calculate the resultant loads in our situation. And also we need to know the centroids. We also need to know the distance for the equilibrium equations. Is okay? I can move down. Okay, so now what we can do is that we can use again equilibrium equations to calculate the internal loads. So we're gonna do summation of forces along x-axis is equal to 0, and all the forces which are acting in this direction are going to be positive. I'm going to do calculation for this section here. I'm going to do calculation for this section here. So we can see this is vertical force, this is vertical force, this is also vertical force, and this is also, so we only have one force, which is the axial force or the normal force acting along horizontal direction, and there is no other force, so I guess that's the result. And if we see from the section 2, there is only one force which is acting on horizontal direction and no other force, so that's what I got from for the one of the internal loads. Now the next step is to do summation of vertical forces is equal to 0, and the assumption we are making, the convention we are doing is that all the forces acting upward are going to be positive and all the forces acting downward are going to be negative. But for this case, we have to calculate the resultant of this triangular distributed load, half of which is in one section and half of which is in another section. So for the triangle, it's going to be easy, but we need to know what is the magnitude at this point, so that, because we can calculate the resultant if we know this distance and this value, we can calculate the resultant force for this triangular distributed load. So we know this, which is 1 meter, but we don't know what's the height. So how we can calculate the height? So I'm gonna draw this whole triangle here, and we know the distance is 2 meter, and we know the magnitude at this point is 200 Newton per meter. And the section was cut at this point, so this part goes here. So we want to calculate the resultant for this force, so we need to know what is the value here. So in order to calculate value at any point, we can use this formula. I'm gonna use y is equal to slope of the triangle, and if this is y, and I will say this is I, or let's just say small l. So if you know the slope of a triangle, then you can calculate the magnitude at any point. So this L we know is 1, but we don't know the slope. So the slope is basically this distance and this distance. So instead of writing slope, I can just say h divided by L. So if we want to calculate what's the value at this point, we can use y is equal to h over L into L. So height is 200, total length is 2 meter, and the distance where we want to calculate is 1. So it comes out to be 100 Newton per meter, which is this point, 100 Newton per meter. And also this point is also 100 Newton per meter. So let's simplify a bit. This distance is 1 meter, this distance is 1 meter, this distance is also 1 meter, and this distance is also 1 meter. This is the force, 300 Newton. This point is 100 Newton per meter. This point is also 100 Newton per meter, and this point is 200 Newton per meter. These are the internal loads, and this is reaction here. Oops. Which is 191.66 Newton, and we have a force here, reaction load here, which is 91.66 Newton. This is N, this is V, this is M, this is normal force, shear force, and a bending moment force. All we need to know is the resultant force so that we can replace a triangular load with a resultant force. And how we can calculate this force is by using the area of a triangle, which is 1/2 into length. Length is 1, and the height, which is 100. So the force is 50 Newton. And we also need to calculate the resultant for this. So this is a trapezoidal shape, and we have a formula for trapezoidal shape, and we also have a formula where what is the centroid for this trapezoidal shape. But we can make our life easy by dividing this shape into the shapes which are familiar, which is, if we divide, we can make a shape one triangle, and this shape is rectangle. So we know this height is 100, so this height is also 100, and this height is also 100. So in this way we can calculate the resulting forces. So for the triangle, this is going to be the resulting force, and for the rectangle, this is going to be the resulting force. So let's try to calculate what is the resulting force for a triangle. So for triangle, it's half into length. Length is, we know, 1, and height is 100 for a triangle. So for a triangle, we get 50 Newton. And for rectangle, the area of rectangle is length into width. So length is 1 meter, width is, which is also 100. So we get 100 for rectangle. So this is the situation right now. So we have a force 300 Newton, and then we had a triangular distributed load, but we replaced this triangular distributed load with a point load instead to simplify our life. That's 50 Newton. And here also we did the same thing. We, instead of using the trapezoidal load, we have used two forces. One is triangular and one is rectangular. So this was rectangular, and this is 100 Newton, and this is triangular, which is 50 Newton. And we also have to calculate the distances where these forces are acting. So they act on a centroid, so we have to calculate this distance as well. So since it's a triangle, so the formula is 2/3 of the length, whatever the length is. The length is 1 meter. So the distance comes out to be 2/3 meter. Similarly, we have to calculate the distances for this two forces as well. So this is a rectangular load. So we know this distance is going to be 0.5 meter because it's a rectangle. So the force acts at a center of a rectangle. But for a triangle, the distance is going to be 2 by third of whatever the distance is, which is 1 meter. So we have 2 by 3 meters. So these are the distances, and these are the forces. I'm going to circle out the forces, and these are the distances. This was our reaction force. This was our reaction force here. And we did a section cut here. So we exposed the internal loads. And these are the directions I'm always going to use. Whenever I will select the left section of a member, I'm going to have this direction. And whenever I'm going to select the right side of a section, then the directions are going to be opposite. So this is normal force or axial force, this is shear force, this is moment, this is axial force, shear force, and a moment. So we know the normal force comes out to be 0 in our case. So now we're going to use second equation of equilibrium, that is summation of forces along y-axis is equal to 0. And we'll assume all the forces which are acting upward to be positive. So if we use this section here, we have this force which is acting downward, so it's negative 191.66. And then you have this force which is acting upward, so it's positive 300 Newton. And then you have this force which is negative 50, and shear force which is negative V, because shear force is acting downwards, so it's 0. So if we solve this, we're gonna get shear force value. So the shear force comes out to be 58.34 Newton. We can also use the right section, and we can also calculate the shear force using this section as well. But the result is going to be the same, like we should get the same value. So we can try. So this is the vertical force which is acting upward, so shear force in this case is positive. And then we have a force negative 100, then we have another force negative 50, and then this is force is acting upward, so positive 91.66 is equal to 0. So if you solve this, you should get the same value. If not, we had made some mistake. So now only moment is left to be calculated. So we'll use third equation of equilibrium, that is summation of moment is equal to 0. So what we can do here is that we can take a moment at any point, but let's just take a moment at this point. And we're going to assume all the moments which are acting counterclockwise are positive and clockwise are negative. So I'm going to take moment at this point for this section. So you have this force is going to be 0 because the moment arm is 0. So let's just talk about this force. This force is going to cause an anti-clockwise rotation at the support A. So anti-clockwise or counterclockwise is positive, and the force is 300, and the distance of this force from point A is 1. And then we have another force which is going to cause clockwise rotation. So clockwise is negative because it's going to make a clockwise rotation at the point A. So it's negative, force is 50. We have to calculate the distance from point A to this force. So this is 1, this is also 1, and this is 2 by 3, this distance. This distance is 1, this distance is 1. So it's going to be 1 plus 1 plus 2 by 3. That's the moment arm, what I'm getting. And then you have this force, shear force. Shear force is going to cause clockwise moment, so I'm going to put negative sign. And the force is V, shear force, and the distance from point A to B is 1 plus 1 plus 1. And then you have a moment which is anti-clockwise, so I'm going to put positive M. So that's yes. This one? Yeah, so we have cut a section here, so we are not going to talk about this. Like whenever we cut a section, we have exposed the forces. So we'll only do the equilibrium equations in this section. So you can ignore that section for the calculation of internal loads. So once we have cut a section, the remaining section we're just going to ignore, and we're going to just do the calculation based on the section we have. Which one? Which one? This one? This one? Yeah, yeah, yeah. Okay, okay, okay. No, because you have, we are taking moment at this point, A, right? So, yeah, so you can put the force 191.66, but the distance from where we are taking the moment to that point is basically 0. So it's gonna like cancel out later. Yeah. So we have 300 minus 50 into 2 by 3. It's 2.67 minus, we have already calculated the shear force, which is 58.34, and this is this 3 plus M is equal to 0. So it's going to be 300 minus 50 into 2.67, which is 133.5 minus 34 into 3, which is 175 plus M. So if you solve this, you're going to get the moment value and if you will solve, you can also solve for section 2 and you should get the same result. maybe you guys can calculate when you go back home, you can calculate the moment at the right side and it should give you the same result. So that's the final answer. So whenever we have to calculate the internal loads, the first step is to draw free body diagram, and then we have to calculate the reactions by using equilibrium equation. And once we have the reactions, then we can cut a section, expose internal loads, and then we can use equilibrium equations again, and we can find out the internal loads.